So my name is Dr. Billy Wu. I'm an associate professor at Imperial College London in our Dyson School of Design Engineering, where I'm also our director of research, and I also chair the Faraday Institution's Training and Diversity panels. So training is very much a passion of mine.
I'm Tal Sholklapper. I'm the CEO and co-founder of Voltaiq. Early career working as a researcher as well. Started my career at Berkeley and Lawrence Berkeley National Lab. Spun out a fuel cell company and got to take that technology from the lab to manufacturing to field trials. So I've seen teams really across that spectrum and how they're dealing with these variety of challenges in the battery sector and fuel cell sector.
So in this talk, I'm going to talk about addressing the battery talent shortage with interdisciplinarity. Firstly, a quick plug for the research group that I co-lead, which is called the Electrochemical Science and Engineering Group. We position ourselves at the interface between fundamental science and engineering application of electrochemical devices. So we do work on lithium-ion batteries, hydrogen fuel cells, supercapacitors, emerging chemistries for energy storage, which is all underpinned by capability in microstructural modeling, understanding and modeling these devices with physics-based models, machine learning algorithms for digital twins, and also understanding manufacturing processes as well. So if you're interested in finding out more about our work, we've got a website where you can see some of our papers and opportunities in our research group. First of all, I just want to start off with a quote which I quite like, which goes, "The Stone Age came to an end not because we had a lack of stones, and the oil age will come to an end not because we have a lack of oil." And I think we've seen a few boom and bust cycles within batteries, and we're going through this unique period of batteries where maybe there's a few shakes along the way, but I'm fully confident that we will fully transition to this net zero future. And just because oil prices fluctuate, the demand for batteries will inevitably increase, which necessitates this decrease in oil. I also like this quote because it was said by a former Saudi oil minister. And I don't know if he was a former Saudi oil minister because he said this, but it's still quite a nice quote to get started with. Within that context of transitioning to our net zero future, I do envisage that everything and so many different devices are going to be electrified. So road transport, electrification, and decarbonization of our electricity grid. And to enable that, we're going to need a lot of batteries. So this forecast data from Benchmark Mineral Intelligence forecasts that by 2030, we're going to reach about 9 terawatt hours worth of battery production, with over 400 battery gigafactories already in the pipeline. So this isn't just forecasts. These are actually announced gigafactories which are going to get scaled up. So that's a lot of batteries. About 2/3 of those will be in China, but the geographical spread will likely increase in the future. So with that 9 terawatt hours worth of battery production by 2030, there's been a few reports out there. So the Volta Foundation report, which I highly recommend, estimates that about 35 to 160 jobs per kilowatt hour battery production are likely to emerge from that, which can broadly translate to about 300 to 1.4 million jobs, obviously across different job sectors. But people will be essential for this transition to a net zero future. And I think when we reflect on making batteries, we also need to think about making better batteries as well. And I often think of this as a multi-length scale, but also multidisciplinarity problem. So we have current chemistries like NMC, LFP, which are predominant now, but there are improvements that we need to make. So we need chemists who understand new chemistries that we might move towards, which are more sustainable, lower cost. Chemical engineers who then understand how to take that fundamental chemistry, scale it up to make into the morphologies that we want to get ideal power characteristics and so on, and how to manufacture electrodes with the right porosity and so on, to manufacturing people who understand how to then assemble these electrodes into cells with ideal contact resistances, different form factors, which one's the right one. And as we integrate these cells into battery packs, which often contain hundreds, if not thousands of cells, we need mechanical engineers, control engineers, thermal engineers, all kind of understanding the various challenges along the length scale and working together. So hopefully that kind of sets the scene for this and what we need in the future for these people to drive it forward. And within making better batteries, we also need to consider how the battery industry is really interconnected. So beyond just making batteries, we need to supply the raw materials. So we need mining and refining people to consider the purity of supply, the ethics of that supply. Then how do we process those raw materials? So whether you start from a hydroxide or carbonate, the spodumene, these all influence the purity and the quality of the precursor material, which then goes into making electrodes where you might have binders, additives coming together. And I think as you go to scale as well, how the mixing process at the industrial scale influences the performance. That's something within a university is often quite challenging to get access to these large scale facilities, which often have very different characteristics to the lab scale resources that we often use. And then segueing to cells, how do we do formation at scale? These are lots of emerging questions which relies on understanding multiple disciplines across multiple scales. And this is true for modules, packs, and ultimately recycling as well, where we have to think about circular economies, and that's where policymakers come in. So you can see that making this battery industry will require lots of people, but also a very multidisciplinary challenge. And I think one thing that I really want to highlight is that as we make batteries, we really need to solve the and problem. That this is a list of 8 key criteria that here in the UK, we have the Faraday Institution. We've articulated that we want to hit. So cost, energy density, safety, lifetime, temperature, predictability, and recyclability. And the reality is it's relatively easy to make a battery which is relatively low cost, but has poor characteristics in these other fields. So we need to also think about making batteries which are energy dense, but also cost effective for that mass market approach as well. And that's what I mean by this and problem. And really, if we integrate this kind of interdisciplinary approach where we understand the large scale challenges, I hope that we can avoid this subsystem optimization trap where maybe we make this fantastic energy dense material, but it just costs an obscene amount of money. So we need to factor that in from day zero, from my perspective. A nice example as well is that I think academia, which I'm an academic, sometimes we look at the theoretical performance and we get very excited, but we also have to consider practical considerations. So here we've taken an example of a solid state battery where if you just took the theoretical maximum performance, you get some crazy energy density numbers where maybe you're over 1,000 watt-hours per kilogram, where traditional lithium ion that you can buy right now might be 250 or something like that. But when you start to consider practical constraints with state of charge or ranges of stoichiometry that you can access, it decreases. Once you include the practical amounts of electrolyte, it decreases as well. Adding in things like current collectors, tabs, and so on, and the housing, all of these things ultimately reduces the energy density. Of course, we can optimize that, but it requires having this holistic understanding of the problem which we want to communicate to all the people in the field. So really that kind of sets the scene to some of the challenges that I think within the battery field, there's a lot of potential subsystem optimization traps where we optimize one thing but ignore something else, which is a broader challenge. I think, as we've mentioned, the battery industry is becoming increasingly interdisciplinary in that we need to consider mechanics with electrochemistry, with electrical engineering considerations. And most of the educational offerings we have right now are single disciplines. So you study chemistry, you study material science. There's an increasing need to consider all of these factors in these real world systems. And I think this is a real problem in things like pack engineering, where traditional subjects like mechanical engineering don't traditionally have electrochemistry in them. So those are some of the challenges, which might then lead into opportunities. So I think there is opportunity for developing new massive open online courses, so MOOCs as we call them, which provides asynchronous learning opportunities. So as you're in industry, can you segue from one industry to another? And I think one excellent example is Gregory Plett's Coursera course on battery management, which I highly recommend. And I think there's an opportunity to develop problem-based learning activities as well. So we don't want to just teach this as a course. Can we do practical things like get engineers and scientists together to develop things like practical electric vehicles? So we have an event called Formula Students, where we get students to design, make, and race zero-emission vehicles, which brings together mechanical engineers with electrical engineers, which I think is an excellent example of that. But also bridging science and engineering disciplines, academia and industry, I think there's huge opportunity there to also integrate knowledge from outside the battery industry. So the paint industry has been around for a long time. What can battery manufacturing learn from their techniques and opportunities? So I think these resources will be shared afterwards, but I highly recommend Greg Plett's battery management courses and books that he's got. University of Aachen provides loads of fantastic primers on manufacturing, battery packs and materials. My own plug for some of my own YouTube material that I share. I think there's some fantastic resources out there, so do check those out. And finally, just to wrap up, I think we want to link up fundamental research with scale up, and I think that's super important. And we get very excited about gigafactories, but I think gigafactories are also gigabucks as well, that are really expensive. So to get a technology from fundamental science breakthrough to actual deployment in vehicle can take over 10 years, and it can cost a lot of money. So really, this is a UK-centric look on it, but I think the pace of action does need to increase to capture this once-in-a-generation opportunity. I think next-gen technologies have some fantastic opportunities to electrify loads of different modes of transport, planes, trains, and automobiles, but we need the talent to drive that forward. In the UK alone, we produce about 1.6, we could produce 1.6 million vehicles, so that could translate to about 270,000 jobs. There is a real economic impetus to really get this right from the very beginning. And my final point is we talk a lot about interdisciplinarity, and I just want to highlight that conceptually, a lot of fields work in a very disciplinary approach. Chemists work with chemists, material scientists work with material science. You might have multidisciplinary teams coming together where there isn't much cross-pollination. They have a grand goal and you bring together these teams, but interdisciplinary, that's really where we blend together and blur these boundaries. There's also a field called transdisciplinary where stakeholders are much more involved in that. We can talk about the nuances between that, but broadly speaking, I think bringing together different disciplines is the core thematic understanding of our approach. And then the final plug is that for people interested in battery careers, as I mentioned, I chair the Faraday Institution Training and Diversity Panel. We created this resource called the Faraday Battery Careers Portfolio, which gives an idea of the various or some of the various roles that are available in the battery industry, how to potentially get into them, some of the activities which could help you get involved. So it's an open and free resource for people to access. So I encourage you to have a look at that. So some of the key takeaways, just to set up the Q&A, is that I do think we've got a once-in-a-generation technology transition, and batteries will be the key enabler for that. And there is a global race to secure this battery industry from raw materials all the way to applications. We do need innovations which are going to be driven by talented individuals, and we need to really avoid the subsystem optimization trap, because ultimately, if we fail there, then those gigafactories are going to be really expensive mistakes. And opportunities that we might want to think about is rethinking how we do our training. MOOCs, are they the way forward? Problem-based learning, bringing together science and engineering, as well as drawing in insights from other fields as well. So if you're interested, I've written a perspective on battery talent, but also welcome discussion in this webinar. So I think that's it for me, and looking forward to all the conversations.
Awesome. Thank you, Billy. And yeah, just as a reminder here, we'll be taking Q&A from the audience. So feel free to put in any of your questions that you want us to discuss live here. And then, yeah, just going to one of the questions I got on the side on the text as well. Feel free to do that too. But yeah, I think there's a lot of anxiety right now in the battery space, just around China, electrification, where it's going to happen, all that. And I think Billy hit the nail on the head. We are entering this magic golden era. I think we finally have an abundance of cells that are low cost and are high performance. Quality is going to be one of the key challenges. So you have to figure out how to make sure you make good cells, but at these price points that no one thought was possible for multiple years into the future. All of these applications that everyone previously said, oh, batteries are too expensive for those, that is no longer the case. So the economics are really here. Economies of scale are really a one-way road. So it's one of those things. There's plenty of lithium. People are actually slowing down some of the mines. There will be more that come online. And so we are entering this golden age. And really the key here is, especially for outside of China, figuring out how we could leverage that and how we could bring the right skills together in order to compete going forward. So With that, I'll just open it up with the first question here. Just really, there are a whole range of fields and expertise from mechanical to electrical to chemical to process engineering. What are the emerging skills that you're seeing, Billy, that companies are looking for as they go in the sector?
Yeah, great question. So I think the field's evolving quite a lot, and I think we want to be more productive with what we've got. Here in the UK, we have an objective to be more productive, which means per hour of time that we work, because all of us have a fundamental constraint that we have 24 hours in the day. So there's a limitation to how much work we can do unless we're more productive. So I think emerging skills in that sense are things like digital skills. So are you now able to do programming? Create simple scripts that help you with data processing, which Voltaiq, I know you're very well adept with. And I think thinking about where there's inefficiencies there, I think there's some really exciting work on automation of science as well. We've seen some really exciting work with using robots to basically make coin cells and pouch cells to get better statistical significance. I think we're going through a phase where we actually need to start to deliver with the technologies. And I think one of the challenges I've seen in the battery industry is that sometimes people often show hero cells where you might make 100 cells, one of them by pure miracle has got good performance, and you show that. But now it's not a case of can you make that hero cell? It's can you make that consistently at a low cost with a low failure rate? Because actually, as you've seen, the repercussions of a battery fire are so significant. And it's almost like an inverse lottery ticket now in terms of thermal runaway. But when that does occur, it's catastrophic, right? So I think if tools such as skills such as programming, computer skills that really harness your productivity, automation, I think these are some emerging skills that we want to think about enhancing traditional industries like material science and chemistry.
Awesome. Yeah, and I could. It's funny that you brought up the hero cells as well, and I think both in the R&D scenario and in the manufacturing scenarios, that is one of the common gaps is the lack of data or the lack of tools to do large scale analysis are really key limitations to scaling up in multiple ways. In R&D, if you're only looking at small sets of data in Excel or Igor or MATLAB, whatever your weapon of choice is, it's easy to find that hero cell and get really excited. But if you start looking at larger populations and looking at correlations or looking at the broader group of cells that came from, you start figuring out where the issues are or starting to realize that's much more complex of the story. Similarly, in the manufacturing scenario, you do get a range of these disciplines from people doing upfront QA in the factory on materials QC and particle size distributions to process engineers and automation engineers who are in the middle layers there. And then the back end, you get the quality engineers and battery engineers looking at the data. And they do look at things different ways. And the challenge is a lot of that, what they do is very siloed. If you go to a battery factory, it's not a single factory, it's actually multiple distinct mini factories within there that there's the electrode, there's the assembly, there's the end of line. And those are each mini factories and they often have different data silos. And unless you collect those, it's really hard to have the different disciplines, let alone the different teams really communicating in the same language. Yeah, so let me expand a little bit and let's talk about more of the interdisciplinarity, which has really resonated with me as soon as I read that term here. I just remember all the conversations with the car companies, and we've got a bunch of great mechanical engineers and electrical engineers, and it's hard for them to wrap their heads around the challenges of electrochemistry, the sensitivity and environment and all of that. There's a lot of this early belief on batteries essentially being this black box in a lot of ways, the source and sink of energy. Um, how do you think about really applying and building up that knowledge across teams that come from these different backgrounds?
Yeah, great questions. I think you're completely right that sometimes there are silos and it's someone else's problem where, let's take, for example, lithium metal, where I think is very exciting in terms of theoretical performance, but there are all sorts of challenges with the mechanical expansion of the material and the whole range of other factors, such as how do you handle that at scale as well. And people often assume someone else will solve it. The way I would see this is, as I mentioned in the talk, problem-based learning. If you set a team a task of saying, okay, let's design an electric vehicle as the application-inspired task for learning, then I think that naturally starts to bring together some of these emerging challenges where you say, oh, okay, we could do this, but actually we need to think about mechanical constraint on our battery pack. How would the battery management system work there, the state estimation, and so on. So that's one way to start that conversation. And I think the first thing is generating awareness of these challenges. I've seen so many times where people aren't aware of the other problems there. I think it's very challenging for everyone to be an expert in everything. But perhaps a T-shaped approach for people where you have that broad understanding of the challenges. You might not be an expert in control, but at least you can start to talk to someone in the field which has that understanding. You share the same language. I think sometimes, say, for example, in the control field and the chemistry field, they use very different languages. We love acronyms as well, an XPS and an SEI and an SOC. For someone getting into the field, that can be very difficult to come in. So I do encourage people to think about the language that they use to communicate these challenges there. So that's the way I would approach this problem. Problem-based learning will focus on getting people talking to each other and realizing that maybe you're talking about the same thing, but using different languages or abbreviations.
Awesome. And then we have a couple questions here about people earlier in their career, thinking about their career tracks. Does a PhD in one discipline matter versus another? How do you really position yourself? And yeah, interested in getting your thoughts, and I have some perspective on that as well.
Yeah, great question. The Faraday Battery Careers Portfolio was specifically called a careers portfolio for a reason. So you'll see a lot of resources which are called career pathways. And I think sometimes in academia, it almost implies this kind of singular track where professor is the end goal. The reality is it's a big pyramid, not calling academia a pyramid scheme, but basically for the number of PhDs that you have, there will naturally be fewer postdocs and fewer academic positions. And the reason why we framed it as a careers portfolio, which implies that just like you might have a portfolio of different activities, we want to encourage people to think about their skill set, that everyone's unique, everyone will take a different career route. And you want to be building up your profile. Like, I've done a bit of programming here, I've done a bit of manufacturing synthesis here. And we want to encourage people to think about moving fields as well, because I think there's a lot of benefit from doing that. But the narrative and the wording that we often use can be very challenging. I think thinking about that earlier and getting industry and academia talking to each other more is really important. To give you one tangible example, I think how we perceive intellectual property or IP is very different to industry. In academia, it's very much, I did this and therefore I own this. From conversations with colleagues in industry, I think it's a lot more about it's the company and you work within a whole team to achieve that benefit for the company. And I think there are some conceptual differences there. I've heard a lot of companies when they do their interviews that half the time it's technical, but then the other half is soft skills. And I think in academia, sometimes we don't focus on those soft skills as much as we should do in terms of how do you work well in teams, how do you communicate with different stakeholders and so on.
Awesome. Yeah. And I think I was very lucky early in my career to, even in undergrad, when I started working at the national labs, the first projects I worked on were industry sponsored. And that was really helped color a lot of how I approach things. And I think part of, just guidance I give people is the PhD in education you're doing, you're most likely not going to use exactly what you learned there. It's just teaching you how to think and how to go about problem solving. And I think just having that kind of mindset, especially going into a factory where there's all kinds of new things coming at you every day, it's learning how to think and how to problem solve is probably the most important thing you could focus on. And then really, I think as Billy said, try to find those cross-disciplinary groups, go and spend some time with another department while you're there. If you can, go get an internship or a co-op or something like that to actually get hands-on experience. Do that as early as you can and start building that capability, and don't stress out about, it's not worth stressing out about, I'm getting a PhD in the wrong segment, or master's or whatever it is. Just go out there, and it's the ability to think and find those opportunities to push yourself in new areas. Awesome. And so I think there's a lot of questions now. I think there's a tremendous opportunity around these online courses that you could really start teaching yourself what you could work. We could learn things online that otherwise would be very hard to get a grasp on. But I've also found that there is a need for that hands-on learning as well. And really interested in your thoughts on that balance between, real world experience and, leveraging the online tools and the power they have as well?
Yeah, great question. I think MOOCs are great for a number of reasons in terms of they scale quite well. They're asynchronous as well, which basically means you can take it at your own leisure. I think we also want to create a battery industry which is diverse and therefore accepting of people with their own circumstances. So if you're working a full-time job, maybe you don't have time to attend lectures which are at a certain time. So I think that's one of the key advantages there. But you're completely right that whilst you can do quizzes and things like that, there is a certain element around working in teams and talking to people, brainstorming different solutions that is difficult to replicate. I think my thinking around how we should approach this is to provide this kind of raft of different resources available to people. It's relatively inexpensive to do MOOCs in that sense, which I think is fantastic. I think when you do these in-person elements, they're a lot more costly, but equally, there's a lot of benefit to do that. So I would look at it in terms of having both is beneficial. If you can integrate more of that physical element, I think that's fantastic. We often run things called hackathons where within a day you set a task, bring together people, and it's not necessarily getting the final finesse product, but it's that process of quick and dirty, and let's pull things together, let's ideate and build a degree of resilience where it's okay to fail.
Awesome. And then, yeah, for those that are in continental Europe or the UK or the US, there is a large amount and growing pilot lines that are there for both industry and academia. A lot of them do run educational courses. We help teach the battery manufacturing short course at Michigan. RIT does a lot of stuff in the US as well. There's a whole range of additional pilot lines. In the UK, there's UK BIC, Warwick, there's others as well. In Germany, there's a whole range also. And so just reach out to those or ping us. We can see if we could connect you and just see the opportunities for educational content or just getting your hands on and dirty and seeing what a battery production line looks like as soon as you can as well. And yeah, so we have a few questions around battery technology. Is there anything that's really catching your eye right now, Billy, in terms of new technologies, chemistries, et cetera?
There are many things that catch my eye. Maybe first a look backwards that I think I'm very keen to see beyond the hype as well. And I think it's important that we put numbers to things. I mentioned a few exciting technologies like sodium ion. And I think sodium ion is an interesting one because, yes, the narrative is that sodium is cheaper and is more abundant. But when you have that holistic look on technologies, we call these things lithium ion batteries. But if you actually look at the bill of materials by mass, it's actually very little lithium in there. And because lithium prices have decreased so much, it goes back to your comment earlier that no one thought we could make batteries so cheap. And actually, the price of batteries is so low right now for lithium ion batteries that the economics for sodium ion batteries isn't quite right now. And I've seen a few sodium ion battery projects stall a little bit. I'm sure there'll be a place for that in the future. So I would first look back and say, what are the practicalities with these different technologies in terms of does the fundamentals actually make sense? If actually most of your cost is in the cathode, should we not be looking at that first? One thing I saw recently that I thought was really interesting is that there was a recent Nature Sustainability paper which looked at new types of cathode materials, which were maybe like 2% of the cost of lithium cobalt oxide. I think once you make a materials that low cost, it changes the equation in terms of what you can actually achieve with the technology. And I think cost, we often get very drawn into high energy density, but low cost, I think that's really the enabler for these real world applications. Because sure, we can put some exotic materials into stuff and that's not too difficult, but I think really getting low cost, that's the key to making real world impact.
So yeah, and on my side, I love the new technologies, the new chemistries, the sodium, the sulfurs, solid state, all of that fun stuff. And I think the one guidance I'd give on that front is really, as Billy said, just really understand your fundamentals, not only on the cost side, but on the other side, really what are your advantages versus now this, low cost commercial product, which is the lithium iron phosphate battery, and how do you compete against that? And so really mapping out what are those applications you're going to go after initially as you try to achieve scale, and really differentiating yourself and having a clear pathway to commercializing the technology is really the key. And I think this next generation of battery companies are now very hyper focused on that and not just build a giant gigafactory and go for it, essentially. And then on the other side, I think the thing I'm really excited about is not only now we've achieved cost, the next real challenge here is quality. There's a lot of implications with these batteries that we're trying to deal with on the back end once they're made because of quality issues and variability in the production process. And that's the BMS needing to balance all the cells. There's end of life issues that happen, system overbuild, minimizing performance and limiting it. And a lot of that is coming from, yes, we've manufactured these, but we're still not manufacturing them super well. And there's a decent amount of variability still in that production process. So one of the areas I'm really excited about is just leaning in on the production processes, and whether it's better understanding of these processes, more metrology, more analytics, really starting to dial in the quality of these cells. Because if you do that, it's going to decrease all the end costs in terms of integrated into a system and all of the lifetime costs going forward. So yeah, the new technology is awesome. Just make sure you lay out the right pathway to commercializing those and be realistic. And then the other side of it is we've achieved scale, and it's going to be more scale and higher quality is ultimately what's going to win here in the market. Awesome. I'm doing that final scan of Q&A questions. Yeah, if you had one final takeaway for the audience in terms of their academic careers or even in industrial companies, what would it be for building this interdisciplinarity into your organizations?
Yeah, great question. I personally think the power of networking is just so important. You just get so many fresh perspectives when you just talk to people outside your field. You never know where an introduction might lead to, and the serendipity that kind of emerges. It does require you putting yourself out there. And it goes back to the other point that, yes, we talk a lot about these technical skills, but I think it's just as important, if not more important, these soft skills around how do you work with others. I think batteries are going to be very international. Probably into China makes the vast majority of cells right now and likely will do in the foreseeable future. How do we work best with these people who come from different cultures and different time zones and so on? Because I do think there's a lot. We've gone through this phase where we had globalization, everyone's going to be friends. Now we're going through a very different phase. And I do think there's a lot of benefit of collaboration over confrontation. Obviously, there's a lot of geopolitics politics to consider, but I do think at the very least sharing knowledge, because we're all trying to achieve the same goal of decarbonization there. So that element of networking outside your circles, not only in disciplines, but culturally as well. I think that's maybe the next frontier that we haven't quite cracked yet, that cross-cultural collaboration at scale, perhaps.
100%. Yeah, so definitely, I just fully advise as well to the networking and those soft skills and being able to learn how to communicate with different cultures, different industries. I just noticed a question here about can you learn from other industries like paint and chemicals and others? And absolutely. And just going back to the early days of lithium ion, Sony, with a lot of the early cells, they went to chip bag manufacturers to figure out the bags for the cells. A lot of this technology has come from other industries, and those who are open are able to not only look at those other industries, but integrate some of the technologies and learnings around whether it's chemicals or process control, or really building that expertise in are really going to be key here. So with that, feel free to email us if you have any follow-up questions. We'll send out the slides and materials. But yeah, really appreciate Billy joining us today for the webinar. And yeah, we'll have the next one announcing very shortly, formally, but we're going to have talking about this next battery industry 3.0. With that's, how to be competitive going forward with these economies of scale. We're going to have a couple different companies talking about their transition. One is going to be Peak Energy, which is a new company focused on sodium ion and how they're going about that. And then also Novonix, who's building up a US domestic supply chain in North America. And so excited to have them on and how they're leveraging data and other solutions to do that. But yeah, thank you all very much, and hopefully we'll see you on the next one.